Welcome back, everybody, to the continuation of the preliminary example from page 112. So we are looking at the top of page 113 here, and we're talking about the same function that we were on the previous page, f of x equals e to the 2x. And I want to remind you of the series that we found on the previous page. Let's start by just writing it at the top of the page here. And our goal in part B is to get a little bit of insight into what this series is really telling us about the function. Okay, so what we've done down below is we've created a few polynomials that kind of come from this series. Okay, so for example, the formula p1 of x that you see here, 1 plus 2x. Notice that that's just the first two terms of our series. So it's like taking our series and chopping it off when we come to the x term. P2 of x, same deal. We're just taking one extra term and going out until we hit the 2x squared term. P3 of x, same deal. We're going out until we hit the x cubed term, and we could keep doing this if we wanted to. Okay, what I'd like to explore is how do those polynomials, P1, P2, and P3, relate to the function e to the 2x? Okay, so one way to explore that relationship is to graph the function together with the polynomials and kind of see what's happening. Okay, so what they'd like us to do is to see if we can figure out where the P1, P2, and P3 are in the diagrams below. Okay, so the first thing I want to point out to you is that this function f, that's the same in all three of these pictures here. That's just e to the 2x, the function that we started with. The P1, P2, and P3 is the other graph in all of these pictures. I'm just going to highlight those so we can tell the difference. Okay, and can we now pick which is which here? Okay, so starting with P1, 1 plus 2x, which of the three pictures do you think that that would be in? Okay, well, 1 plus 2x is the graph of a line, so P1 has got to be this one. Notice that that appears to just be the tangent line of our function that we started with. Okay, and then we move on to P2. Which picture is P2 in? Well, we can see that P2 is the graph of a parabola, so it must fit this one here, P2. Okay, well, by the process of elimination, that means that the last one must be P3. Okay, and now we come to kind of the critical observation here. Do you notice anything interesting about what's happening with these polynomials P1, P2, and P3, how they're relating to the function e to the 2x? Well, you might notice that P1, P2, and P3 appear to be getting closer and closer to the function. If you look over here to the right, P3, a lot of its graph is almost right on top of the function. So it would appear that we've got some kind of convergence going on here. As we take more and more bigger and bigger values of n, Pn of x appears to be getting closer to our function. So we could maybe say the following. So what we've discovered here is that a Taylor series is essentially a series that converges to our function provided that certain conditions are met. Okay, and that's kind of where we're going. We're going to use this type of series to approximate a function. Okay, so let's move down then to a general description of this. Okay, what we're talking about in this definition is just going to generalize what we just did in the previous preliminary example. It's going to give us a kind of a step-by-step way of building a Taylor series that's a little bit shorter than the way that we did on the previous page. Okay, so the definition that we're writing here is the official definition for the Taylor series of a function, and it's defined by this sum. Okay, that looks a little bit ugly, but if you were to write it out term by term, Okay, just start with n equals 0 and continue up, you would come up with this line. And what I want to point out here is that these expressions that I'm circling, those come from the same formula that we found in the preliminary example. You could look back and see those are just the c's that we talked about. In general, Cn had the form of the nth derivative of our function divided by n factorial. So same thing that we saw on the previous page. Okay, and we'll add one other piece of terminology to this that kind of goes with part B of the problem that we just saw above. Sometimes we'll be interested in chopping the series off and just talking about the first up to the nth power. We give that the name, we call it the Taylor polynomial, Pn of x. That's the same notation that we used above. And basically it's the polynomial that you get by going up in your series until you hit the nth power. That's what the n means when we say Pn of x. Okay, and in a minute we're going to do a number of examples illustrating how we use this formula. One last comment though before we do that, the note down here. A very common value of a to use when you're calculating a Taylor series is a equals 0. And we give the Taylor series a special name. In that particular situation, we call it the Maclaurin series for f of x. Let's write out what that formula would look like if a is equal to 0. Okay, so the series has the following special form in that case. And basically what we do is go back up here and just plug in 0 for all of the a's. Okay, if we do that, we're going to get f of 0 plus f prime of 0 over 1 factorial, and then x minus 0 we could just write as x. Okay, and continuing on, f double prime of 0 over 2 factorial x squared, and so on. Okay, so what we've just written out is what's known as the Maclaurin series, and again, all that is a Taylor series where the number a happens to be 0. Okay, and like I say, we will do some examples and kind of see how this works building a series like this.